Hello everyone, welcome back to the course on measurement and instrumentation, and today is the second lecture of our 10th week where we are discussing about signal conditioning circuits or signal conditioning systems. Today we will continue our discussion on DACs that we started in the previous class. We discussed about few characteristic of DACs, and we also saw different type of DAC circuits. We have seen that how a register string can be used to construct DAC, of course in conjugation with the op-amp, okay. And apart from that, we have also seen two different other kind of DAC circuits, that are R-2R ladders and binary weighted register based DAC, or say n-bit binary weighted register based DAC, depending on how many bits are there in the input, okay. We have also seen what are the different demerits of using a register string based circuits, and one of the major disadvantages that we have seen for a register string based DACs are the number of registers that are used, okay. So when you have that many number of registers, it becomes very difficult to have multiple bits. So mostly we have seen that when the requirement is less than 10 bit, we can go for register string based DACs, but not for all kind of requirements, okay. Let's see another kind of DAC, that is the circuit is known as R-2R ladder, and the word ladder is coming from certain ladder kind of structure of the circuit that we'll see, okay. So as the name suggests, R-2R ladder DAC converts a digital binary input into an analog voltage using a repeating network of only two kind of registers. You have one value is say R and another is 2R. What I mean to say that if you are using R as say 1 kilo ohm, you require another resistor which is of the value of say 2 kilo ohm, okay. So just by using these two resistors, you can design a DAC. So the matching of resistors and requirement of n number of resistors is now minimized. So now you need just two distinct kind of resistors, okay. Now these resistors R and 2R are arranged in a ladder like structure which divides current in binary proportion, and that's why the name ladder has been given, okay. The ladder network together with an operational amplifier produce the analog output, that is the required output, okay. Now just have a look on a basic R-2R ladder circuit. So I have here 4-bit DAC. So these are the 4 bits, and this VA is representing the LSB and this VD is representing the MSB, okay. And you can see the resistors requirement here. You have 2R, R, 2R, R, 2R and so on, okay. Now the ladder word, as I have mentioned, comes from the ladder like configuration of the resistors which is used within this particular network, okay. Now when you have all these bits as 0, means you have applied low to all these bits, say 0, 0, 0 and 0, okay, output expected is 0, okay. Now let us see that how it will be 0. Okay. For that, I have to understand the equivalent resistance and Thevenin voltage of this circuit, okay. Now let's see the equivalent resistance from this side, okay. Now in this circuit, if I call these resistors, say this 2R I am calling R1, this 2R I am calling R2, similarly I have named it like R1, R2, R3, R4, R5, R6, R7 and R8, and they are taking the alternative values between 2R and R. So R1 is 2R, R2 is again 2R, and sequentially I have placed it. So R3 is R, R4 is 2R, R5 is again R, R6 is my 2R, R7 is R and R8 is 2R, okay. Now if I have this kind of configuration, if I want to find the equivalent resistance, now let me call this R1, R2 and R3 configuration this as RA, okay. In that case, RA is equal to R1 parallel to this R2, and this parallel configuration is in series with this R3, alright. So in that case, R1 parallel R2 will be equal to, since both are 2R, so R1 parallel R2 will be equal to R. So I have R in series with this particular R, right. So, I have R and R now connected in series, right. So, this equivalent is R plus R3 is again R. So, RA is basically 2R, all right. Similarly, we can also have look on the other configuration. Now, till this point, which is RA, okay, we have got the value as 2R. Now, this 2R or this RA is again in parallel with this 2R, which is R4, okay, and this configuration is in series with R5, okay. So, you have 2R which is your R4 in parallel with RA, which is 2R. So, this is R4 parallel with RA, okay. So, again RA was, so this was RA was 2R. Now, this 2R is in parallel with this 2R, which is R4. Now, this equivalent is again R, and this R is in series with this R5, okay. So, till this particular point, I have again resistance as equivalent resistance as 2R, okay. Now, this 2R is again in parallel with R6, okay. Now, let me call it say RA bar, okay. Now, RA bar is again 2R, and if I want to calculate the equivalent resistance, again that 2R will be in parallel with R6, okay. And if you calculate this, again 2R is in parallel with 2R, which the equivalent will be R, and that R is again in series with this R, okay. Now, when it is in series with R7, the total resistance, or let me call it RA double prime, as R plus R, and it is equal to 2R. Now, the equivalent resistance till R7 we have got is 2R. Now, that 2R is again in parallel with R8, all right. So, because of that, my equivalent resistance, or I can also say now R in will be, or the input resistance will be equal to 2R in parallel with the equivalent resistance till R7, which was 2R, right. So, this is equal to now R, all right. So, if I solve for RA and all other values, finally, I got R in as simple R. So, all this equivalent resistance or the equivalent resistance for this complicated ladder circuit comes out to be R, okay. So, if I have to represent this circuit in a more simplified way, I can simply say this is just a op amp with a non-inverting input, and this resistance R in is equal to R, and of course, in this configuration you know that V out will be equal to minus RF by R in into V in, okay. Now, as V in is 0, because we have considered that VA, VB, VC and VD all are 0, means we have applied low to all these inputs, okay. Therefore, output will be 0 here, okay. Now, let VA is connected to the reference voltage ER, which is say for example here 5 volt. Now, it is no longer at 0 potential. Now, I have connected it to say 5 volt. Now, let us see what is changing and what will be V out in this particular configuration, okay. Now, when I say this as 1, what I mean to say that I am applying a 0 0 0 1 as input, okay, because I have mentioned earlier that this VA is basically representing the LSB and VD is representing the MSB, all right. So, when I have VA connected to ER or the reference voltage, or here I am taking a 5 volt, let us see what will be the output, okay. And it also means that I am applying digital input as 0 0 0 1, okay. Now, what I have to do is I have to calculate the Thevenin equivalent voltage here or Thevenin's voltage here, okay. So, VTH1 let me calculate for this particular configuration or this particular form. Okay. So, VTH1 will be simply equal to VA, okay, into 2R by 2R plus 2R. So, this 2R plus 2R, okay, basically at this particular point. Okay. Now, VA is equal to 2R plus 2R means that simply VTH1 is equal to 2.5 volt. Okay. Now, RTH1 is again, if you see from this side, is the parallel configuration of this 2R and this 2R, okay, means that I have attached it over here. You can also think something like this for visualizing it in better sense. Okay. It is the same, just I have connected wire over here. Okay. Now, this 2R is in parallel with this 2R, all right, and at that point this RTH1 becomes R. Okay. Now, if I move to point B where I am again applying 0 only, okay, VTH2 will be equal to 2.5 into again 2R by 2R plus 2R, which gives me 1.25 volt, and RTH2 will be equal to 2R in parallel with 2R, which is again R. Now, if I move further, VTH3, okay, it will be equal to 1.23 into 2R by 2R plus 2R, which is equal to 0.625 volt, and RTH3 will be equal to 2R parallel to 2R, which is again R. Now, again if I move to point node D, okay, VTH4 will be again equal to now 0.625 into 2R by 2R plus 2R, and 0.625, please note that it is coming from the equivalent resistance from the previous stage, which was 0.625. Okay. Now, VTH4 will be equal to 0.625 into 2R by 2R plus 2R, which is equal to 0.3125 volt. Okay. Now, V out is equal to 300, just convert this into millivolt, it will be equal to 312.5. Now, RTH4 will again be equal to 2R in parallel with 2R that we have seen earlier also, and it is equal to R. Okay. Now, if you see, this particular value is nothing but 1 by 16th value of the 5 volt supply, whatever I have, or ER you can say. Okay. So, or you can say 1 by 2 to the power 4, where 4 is the number of bits that I am using into 5 or into ER. Okay. Now, this is about when I have input as 0, 0, 0, 1. Now, if say input is 0, 0, 1, 0, okay, or it means that now node B is at high, okay, and other nodes are at 0, okay, that is what it is showing. VA is 0 now or grounded now, and VB is now plus 5, and VC and VD is again simply grounded. In that case, V out will be equal to, similarly you can calculate, will be equal to 625 millivolt, okay, or 0.625 volt. Okay, or if you see this 625 millivolt, it is 1 by 8th or 1 by 2 power 3 into the ER. All right. Now, similarly, when input is now 0, 1, 0, 0, or VC is now connected to high value or say plus 5 volt and others are grounded. Now, this will be equal to 1/4 of the value of plus 5 volt input, okay, or it is just 5 by 4, which is 1.25 volt. So, the output voltage is 1.25 volt when input VC is high. Okay. Similarly, when input is 1, 0, 0, 0 or voltage is supplied now to node D, the output voltage V out is determined to be 2.5 volt, or this is just 1/2 of the ER value, or which was the plus 5 volt input, and it is now 2.5 volt. Okay. So, for a 4-bit R-2R DAC, V out is equal to VA plus 2VB plus 4VC plus 8VD by 16. Okay. Similarly, you can extend it for n number of bits, and for n bit R-2R DAC, generalized equation can be written as V out equal to VA plus 2 VB plus 4 VC plus 8 VD plus 16 VE plus 32 say VF and so on, divided by 2 to the power n. Okay. Now, if you see, the advantages of R-2R DACs are enormous. You are using now only 2 registers value. Now, when you have only 2 registers value, it's very easy to fabricate in a IC also. So, you will see that most common DACs are R-2R ladder based DACs. Okay, they have very good accuracy and linearity, and they are suitable for high bit DACs also. Okay. However, R-2R ladder based DACs has certain disadvantages also. Although you have only 2 registers, then also register matching is important. Particularly if you see, you have one register as R and another is exactly 2R. Okay. So, of course, there is a certain level of matching that is required, and this matching requirement is very precise. Okay. So, this require actually very precise register matching, and this is one of the disadvantages, and particularly when you see from fabrication point of view, sometimes it can also become tedious. Okay. Then you require several switches here also, so that is another disadvantage. You want to avoid switches as much as possible, okay, because if you have more number of switches, switching errors can occur. Okay. So, these are some of the disadvantages, but then also R-2R ladder based DACs are very popular. Okay. Now, there is another kind of DAC which is a binary weighted resistance based DAC, or we also called it n-bit binary weighted resistance DACs. Okay. So, a binary weighted resistance DAC is a circuit that converts a digital binary input into a proportional analog voltage or current using resistors weighted according to the binary values. Okay. What I mean to say by weighted binary values, we will see in some time. Okay. Now, each digital bit controls a switch that connects a resistor either to a reference voltage ER or to the ground, similar to what we have seen in other cases. Okay. Now, the resistors value now follow a binary weighting sequence. When I say binary weighting sequence, means that say first value is say R, I can also write it as 2 power 0, another resistor required is 2R or say 2 power 1, another resistance required is 4R, or you can say 2 to the power 2 into R. Another resistance required is 8R, which is 2 to the power 3 into R. Then another resistance requirement is 2 to the power 4 R. Alright. So, this is the resistance requirements for a binary weighted resistance based DACs. Okay. Now, the most significant bit contributes the largest portion of the output voltage, while the least significant bit, as the name suggests, contributes the smallest portion in this. Okay. Now, this is a typical binary weighted resistance based DACs. You can have a look on this particular configuration. You have these switches SN-1, SN-2 and so on to S0. These are different switches. This is the reference source, and these are the weighted resistive network R 2 power 1 R, 2 power 2 R and so on. Okay. And accordingly the current values are like I by 2 and so on, and I by 2n minus 1. Okay. Now, if you see, it has several components including switches, the feedback resistances, and then you have this weighted resistance network and so on. Okay. So, let us see the components of this binary weighted resistance DACs one by one. The first is say switches. So, if you count, if the DAC is of say n bit, there are n number of switches. Okay. Means that you have one dedicated switch for 1 bit. Okay. So, there are, if you see, SN-1, SN-2, S1 to S0 switches. Okay. Now, there is a resistive network of n registers also here. Okay. So, one resistor is connected in the input circuit of each bit, and the resistances are weighted, means that if the resistance in the circuit for MSB is R, the resistance in the circuit for next significant bit is 2R and so on. So, the resistance in the LSB circuit is now 2n minus 1 into R. Okay. Similarly, you have reference source, which was a requirement for all the DACs that we have seen, because ultimately we want a analog output. So the voltage of the reference source here is say ER, okay, and this reference source matters a lot for DACs, and it has to be a stable voltage supply, okay. Now you have a current to voltage converter here, okay. So it is an op-amp that adds up the current flowing in the resistive network to develop an output analog voltage signal which is proportional to the digital input signal, okay. Now suppose switch SN-1 is connected to the positive end of the reference source and rest of the switches are grounded. Under the condition only MSB is 1 and rest are 0, and in this case the output voltage E0 should be equal to ER by 2 for proportional or a proper digital to analog conversion. So E0 by ER equal to RF by R, we have already seen, okay, or I am not considering the sign convention over here, okay. Now E0 by ER is 1 by 2, that is one of the requirement, okay, because this 2 is coming because you want binary weighted resistance. It can be, say, if it is 1 by 3, you may not get the binary weighted resistance. So E0 by ER is equal to 1 by 2, or in that case, since this is equal to RF by R, RF by R is also equal to 1 by 2. Please note, again I am telling that I am not using the sign convention, I am just using the magnitude values, okay. Now it means that resistance in the feedback resistor of op-amp is basically 1 by 2 or half of the resistance R, okay. Now suppose for a binary input MSB is 1 and also the next significant figure is also 1 and again all are 0. In that case E0 will be equal to 1 by 2 plus 1 by 2 power 2 into ER, or say 0.75 ER, okay. So let's consider that R1 be the resistance in the circuit of the bit next to MSB, then input resistance Ri of the op-amp can be given as R into R1 by R plus R1 because they are in parallel, okay. Now in that case we have already seen that E0 is equal to RF by Ri into ER, okay, or E0 is equal to 0.75 ER, okay. Now RF by Ri, since this is equal to 0.75, okay, and RF we have already seen is equal to R by 2, okay. In that case, if you put this value of RF as R by 2, means that R by 2 Ri is equal to 0.75, okay. Now Ri is equal to R by 1.5 if you just rearrange it, okay, but Ri we have seen as R into R1 by R plus R1, okay, means that R plus R1 by R plus R1 is equal to R by 1.5, or R1 is equal to 2R, okay. Suppose all the bit in a n bit converter are 0 except for the LSB which is 1, and let's consider that Rn be the resistance of the LSB circuit, then in that case the output voltage for LSB E0 for example will be equal to ER by 2 power n that we have seen. Therefore, for proper digital to analog conversion, this E0 is equal to RF by Ri into ER, and in this case, since E0 is equal to ER by 2 power n and RF is equal to R by 2 and Ri is equal to Rn that we have just seen, okay, or we have just considered that the resistance of the LSB is say Rn. In that case, ER by 2 power n is equal to R by 2 into 1 by Rn into ER. And therefore, Rn is equal to 2 power n minus 1 into R, okay. Now it is clear now that if proper digital to analog conversion is to be carried out, the resistive network should be weighted and the weights are something like this. So you have R 2 power 1 R, 2 power 2 R, 2 power n minus 2 R and so on, and then you have 2 n minus 1 into R, okay. Now output current, if you talk about output current I0 will be equal to I plus I by 2 plus I by 4 so on plus I by 2 power n minus 2 plus I by 2 power n minus 1, okay. Now say if all the bits are say for example high, in that case it will be equal to I into 1 plus 1 by 2 plus 1 by 4 and so on 1 by 2 power n minus 2 plus 1 by 2 power n minus 1, and now I is equal to ER by R, or I naught will be equal to ER by R into 1 plus 1 by 2 plus 1 by 4 plus 1 by 2 power n minus 2 plus 2 power n minus 1. And when, as I have mentioned, when this is true only if all the bits are 1, we have considered that all the bits are 1, and in that case the generalized expression can be carried out like I naught equal to ER by R into dn minus 1 plus dn minus 2 by 2 plus dn minus 3 by 4 and so on into d1 by 2 n minus 2 plus d naught by 2 n minus 1, and it's a kind of series, and you can find the value. Alright. So, this is one kind of representation. Another representation of binary weighted input DAC is in this form. You can see that this is a simple inverting summing amplifier, okay, and if I want to calculate this IF is equal to I1 plus I2 plus I3 plus I4, okay, or in terms of voltage, V out is equal to minus Rf by R1 into V in 1 plus Rf by R2 into V in 2 plus Rf by R3 into V in 3 plus Rf by R4 into V in 4. Okay. Now, if all the resistances are equal, or say R1, R2, R3, R4 are equal and they are also equal to the feedback resistance Rf, then each input channel will have a closed loop voltage gain of unity, and the output voltage can be simply given as V out as minus V in 1 plus V in 2 plus V in 3 plus V in 4. Okay. Now, if we now assume that the 4 input of the summing amplifier are binary input with voltages of values say 0 or 5, means either low or high, and we double the resistive values of each input resistance with regard to the previous one, we can produce an output condition which would be the weighted sum of these 4 input voltages. Okay. And based on this, this is one of the example where a 4-bit binary weighted digital to analog converter is shown, and you can see that these resistances are, we were discussing the weightage resistances. Okay. Now, in this case, V out is equal to minus 1 Vd plus half Vc plus 1 by 4 Vb plus 1 by 8 of Va, or you can say that 1 by 2 power 0 or 1 into Vd plus 1 by 2 power 1 Vc plus 1 by 2 power 2 Vb plus 1 by 2 power 3 Va, and that is why I was talking about the weighted resistances over here. Okay. Now, the 4-bit binary code, for example, say 1000 is applied, the output of the DAC circuit will be minus 5 volt, as V out will be equal to minus 1 Vd plus half Vc plus 1 by 4 Vb plus 1 by 8 Va, and as I have mentioned, you have only MSB as 1. So, all these are 0 and you have only Vd left. So, you have 5 volt. Okay. Now, the 4-bit binary code, say for example 010 is applied, and that will produce analog output voltage of say minus 2.5 volt, as you have this as 0. Now, this is 0 and this is also 0. So, you have only Vc as 5 volt, this was high, and then your output is minus 2.5 volt. Okay. Now, this is a simple circuit, but please note that you are using different resistors. They are weighted resistors, but they are different resistors. Okay. Now, advantage of this kind of configuration is they are having a very simple circuit design. So, design implementation is easy. Okay. It has fast conversion speed and it is easy to understand and implement. Okay. These kind of weighted resistor based DACs are suitable for low resolution values, or where your requirement is low resolution DACs, you can use them. Okay. However, they also come with different disadvantages, like they require very accurate resistance values. Okay. Particularly when the requirement is this kind of weighted values. Okay. Now, this is difficult to implement for a large number of bits. Okay. Large range of resistor values are required, and sensitive to resistor tolerance errors is also not that high. Okay. So, these are certain disadvantages of this kind of DAC circuit. Okay. Now, I would say that you have now basic understanding of DACs, digital to analog converter. So, one more important thing that we plan to discuss is ADCs, which is analog to digital converters, and in our third lecture of this 10th week, we will continue our discussion on this kind of converters, and we will discuss the analog to digital converter in our next class. Thank you.